Yo, what up, Year 12? This is our new series on vectors, and this is dedicated to our very own eco warrior, Campbell. So we're going to start with 12A. Now, the exercises in this section go through 12A.1 and 12A.2, and let's see if we can cover both fairly quickly. Now, the first part is just about the concept of what a vector is and what a scalar is. So most measurements or amounts we've used so far in maths have been scalars, which means they have only a magnitude, which means size, okay? Whereas a vector is something that has both magnitude or size and direction. Okay, so for example, if we're talking about the speed of a plane, that would be a scalar, because it might be something like, it goes 200 kilometers per hour, whatever it is. Whereas when we're talking about velocity, for example, that there is a vector because it also includes the direction that you're going in. And it could be represented like north, west, east, south, etc. Or it could be, north 50 degrees west. There's different ways of representing direction. Here are some other examples of vector quantities. So acceleration, because you can go sort of forwards or backwards, or like speed up and slow down. Okay, so there is that idea of direction. Force, displacement, and momentum. So those of you who are studying physics hopefully have come across these ideas before, so you have a bit more of an idea of what they are. So this is how we represent vectors, that we use line segments, kind of like a array, but we call it a directed line segment, or you can call it an arrow. Now the length of your arrow represents the size or the magnitude of the quantity, and the arrowhead shows its direction. Very straightforward. So let's say here, for example, we've got a farmer pushing a post with a force of 50 newtons. Force is actually, I'll highlight that for you. Force is measured in newtons for those who are not familiar. Let me just draw an arrow here for you. Force is measured in newtons. That is the unit of measurement, okay? Just like how, distance is in kilometers, okay, force is in newtons. So pushes it to the northeast, and we can draw a scale diagram of the force relative to like the north line, and there it is. And there is also, importantly, a scale. So in this case, 1 centimeter represents 25 newtons. So the arrow that we've got drawn here needs to be 2 centimeters, okay, to represent 50 newtons, for example. And with direction, and think about your compass bearings and all that stuff you did in year 10 and year 11, we always normally measure from north, okay. So example 1 here, draw a scale diagram to represent a force of 40 newtons in a northeasterly direction. So very straightforward. Let's just do our compass directional crosshairs sort of thing. Now it says we want to go in a northeasterly direction. So northeast is directly in the middle of north and east, right? So in the middle here. But if it's directly in the middle, that means that's 45 degrees, right? Because it's half of 90. And this is 45 in here too. So actually I should put it in here because we measure from north, okay? And we want 40 newtons. So I'm just going to draw an arrow going that direction. We're going to say this is 40, capital N is newtons, but we need some sort of scale. Mine obviously will not be accurate because I didn't do this with a ruler and it's on the iPad. But let's say we choose, 1 centimeter to be equivalent to, 10 newtons. And let's say my line there is 4 centimeters. Let's imagine that that's the way it is. Okay, so that's 12A.1. So please have a go at exercise 12A.1. Let me write it here for you. Exercise 12A.1. And then let's continue. Okay, So this is how we notate a vector. It's important that you know how to use the right symbols and notation. So a position vector, let me highlight this for you, is a vector from like from origin O to some point A. So we usually represent it like this. We write for the capital letters O and A, the 2 points, and then we have this little arrow on top, which means it's a vector, okay? And it goes from O to A. So the arrow head is on the A, capital A point, if that makes sense. And then the vector itself, sometimes they'll call it, here it is, like little a, but it's in bold, which is what is here on the arrow. But obviously we can't bold it when we're writing, so usually you guys will write it like this, A with the little arrow, little a with the little arrow on top, or this squiggly line above it, okay? If we're talking about the magnitude or the length that could be represented by your vector, we put these like absolute value symbols around it, okay? And that just means the magnitude. Or you could write like this, any of these ones, but with those sort of absolute value symbols as well. You could just write OA, though I've found that less commonly used. So I think it's better if you do like the absolute value symbols, because absolute value at the end of the day just means distance from origin. Okay, so remember, if you had learned, I think we learned this, back in year 11 a while ago. If I asked you, for example, the absolute value of 3, that actually means what's the distance from origin if I'm standing at 3. So it's 1, 2, 3, obviously. So it's actually 3. If I asked you for the absolute value of negative 3, okay, it actually means if I was standing at negative 3, what's my distance from origin? 1, 2, 3. So the answer is also 3. So it's all about distance. And so that makes sense here, that we use those absolute value symbols to represent the magnitude of your vector. Okay, some more language. So here if I have a vector AB, and it originates from A, it terminates at B, so that's just the language we use there. And we would say that AB is the position vector of B relative to A. Okay, let's go on to the geometric vector equality. So if you have two vectors, they're equal if they have same magnitude and same direction. So all of these here, okay, they have the same magnitude, so the same like length in the diagram to show their magnitude, and they're all going in the same direction, so we would say that they're equal, even if they're put in a different position on, say, your number plane. So they're parallel, going in the same direction, equal length. That all makes sense. So yeah, it's like picking up the arrow and just moving it sort of left and right and up and down, but it stays in the same, like the same gradient, I guess you could say. You know, they're parallel, so it's like the same sort of slope, and so it's the same direction but also the same magnitude. With vectors though, we can draw them from any starting point, so we can consider vectors to be free, and this is called a free vector. So let me highlight this for you. We can draw a vector with given magnitude and direction from any point, so we call them free vectors. Now, if we're talking about the vector going in the other direction, so it's like this one here in light blue, instead of going from A to B, we want to go from B to A. They have the same length, they have opposite directions. We would say BA is the negative of vector AB. Or you could say, here, vector BA is equal to the negative of vector AB. Okay. You could also use the little bold A and negative little bold little a as well. Okay, but that's really more for textbooks. You guys should use the capital letters for the starting and end points, and the arrow above. Let's do example 2 super quickly. So here PQRS is a parallelogram with vector PQ is little a and vector QR is little b. Find vector expressions for these. So you can see QP, where's QP? QP is going to go this way, isn't it? Okay, from Q to P. So it's we could say that this is also equal to negative little a, yeah? Okay, negative little a, that's bold. I can't do it bolded though, so I think I'm going to have to do like the little squiggly above it. Okay, but it's the negative direction of this one here, right? Okay, let's do B. The vector RQ, so where's RQ? RQ is going this way, right? So it's going to be negative bold little b. Okay, so it's like negative b, and that's the bolded version. And then what about question C? SR. So SR is going this way. Now, can you see that is actually this? It's parallel to PQ. Yeah, and it's the same magnitude because it's parallelogram, so it's actually at the same distance. So you need to remember those features where the opposite sides and parallelogram are equal. So that means it is actually equal to, it's also equal to, you could say it's equal to PQ, the vector PQ, or you could say it's equal to the bold A. Okay, so, but I've done it with the squiggle instead of the bolded. A, and then what about vector SP in question D? Let's have a look. SP is going this way. So you can see it's the same as RQ. So it's the same as negative B. Yeah, so that'll be, we could say it's the same as RQ. Yeah, that's right, which is negative B. Okay, and that is what you guys need to have a go at for exercise 12A.2. Please have a go, and let me know if you have any problems. Now that is on page 278 in your textbook. There we go.